For our last lecture, we're going to consider the second law and entropy balance applied to open systems. So it's going to take probably less than 10 minutes of a theoretical development, and then we will work some examples. So let's take a look at closed systems first, a quick little summary of an entropy balance for closed systems, and then we're going to adapt that to open systems. So as a summary, we started with the Clausius inequality, and then we're able to show that delta S, so this is capital S, extensive property is greater than or equal to the integral of dq over t. This is evaluated at the boundary where the heat transfer is occurring. So what we've done is added this entropy production term, or entropy generation, entropy production, to balance out this inequality. Alright, okay, so if sigma is equal to 0, then this is the internally reversible case. If it's greater than 0, then that satisfies this inequality, and it's a physically possible device. It satisfies the second law. If entropy generation is less than 0, it violates the second law. So that's the idea of entropy production, is to force that to be a balance in the equation. Okay, it can be kind of tricky to evaluate this term. However, if the boundary temperature is not changing, if that's a constant, then that comes outside this integral, and you integrate dq, and you just get q. So that term can be replaced with q over the temperature of the boundary. And then to generalize this, we could have a couple of different heat transfers at different locations occurring. So the boundary temperature at that location could be different. So you just kind of have to keep those organized. What's the boundary temperature where the heat transfer is occurring for each of these? Sum them all together in the entropy balance before. So this summation of Q over T boundary, so K is just referring to which particular location where the heat transfer is occurring. Add all those up. Solve this for sigma, so take that to the other side of the equation. Here's our entropy produced within the system. It equals to the entropy change of the system, so M times S2 minus S1. It's a closed system, remember, so there's one mass, minus the summation of Q over T. And that is a boundary temperature has to be absolute. So the second law says that that has to be greater than or equal to 0. So there's one equation. We could put a box around that equation. And again, this is only considering the entropy being produced inside the system. We could then come up with another equation that would work. A lot of times this is more convenient. We're going to consider the system plus the surroundings as a composite system. So all of this, here's our system inside, all of the immediate surroundings we're going to treat as a thermal reservoir at a temperature T of the surroundings. So the outside of this system would be adiabatic. So if we take the general equation above, apply it to the composite system, so delta S here now applies to both components, the system plus the surroundings, and then this composite system is adiabatic. Alright, so that term is gone. I'm now also going to call this sigma isolated, because if we do this composite system, we're treating that as an isolated system. So sigma isolated is equal to delta S of 2 parts is all that's left in that equation. This equation is gone. So we need this for the system, which is easy. We already know how to evaluate that. We simply need to evaluate this for the surroundings. So considering this for the surroundings are effectively a thermal reservoir, so T surroundings is not changing no matter which way the heat transfer, out of the system into the surroundings or out of the surroundings into the system, either way. So from the perspective of the surroundings, this is reversible heat transfer, so delta S is just Q over T. So in this case, Q of the surroundings over T of the surroundings, because we're trying to evaluate delta S of the surroundings, and then we can actually express Q of the surroundings in terms of the system. Whatever is coming into the system is coming out of the surroundings, and so you just add a minus sign and then change that to a system. So we can still define this Q to be expressed with our sign convention relative to the system. Okay, and then again, there could be several surroundings, right? We could have a reservoir down below, a reservoir up high, different heat transfers. We could keep that straight with the summation. So we have a very similar looking equation. Sigma isolated is equal to delta S of the system. So that's again M. This is M S2 minus S1 for a closed system, and Q system over T of the surroundings. That's a minus sign. So this has to be the absolute temperature of the surroundings. So the only difference between these two equations, let's see if I can get them both here. This equation, temperature, looks exactly the same, except that's temperature of the boundary. This equation is temperature of the surroundings. So this number, sigma isolated, is going to be a little bit larger because this sigma produced, or sorry, entropy produced accounts for the entropy being produced in the system plus the entropy being produced in the surroundings. So this would be called the total entropy produced then, or delta S total, as a consequence of the existence of that system. Whereas up above, this sigma would be the entropy produced only within that system. So globally, there's actually more entropy produced than this. There's some produced because of the interactions with the surroundings. There's some produced in the surroundings as a consequence of that system. Okay, so two ways to evaluate depending on what information you have. We can check this, sigma. So the entropy produced within the system, that has to be greater than or equal to 0. Also sigma isolated, or the total entropy produced, has to be greater than or equal to 0 also. So that's the two equations. We can put a box around this one as well that we have for closed systems. So now let's take, and we've already worked a couple of examples, but let's take that and expand it, apply it to open systems. So we'll take that closed system result to start off with, delta S total. So this is the same thing as sigma isolated, delta S of the system minus Q over T. That's greater than or equal to 0. Let's change this and apply it on a rate basis. So just divide by dt on an instantaneous rate basis. ds total dt, so this is the production, so this would be sigma dot isolated here, is equal to the rate of change of the system entropy minus, now this Q has a dot on it, so this is a heat transfer rate rather than the total heat transfer that has occurred during a process as this one. This is a rate, so different dimensions between these two. Everything else on the equation is the same. We're just dividing through by delta T, making that a rate basis. Also a little reminder that this is actually ds dt of the surroundings, treating the surroundings as a thermal reservoir. Okay, what's inside here, the ds dt, that's due to the change in the state of the mass inside the system. Right, so up here that was M S2 minus S1 for a fixed mass. All we're going to do now is recognize that that mass in the system, we want to convert this, instead of expressing that in terms of a fixed mass, we want to express this in terms of a control volume. And in a control volume, the mass is continuously being replaced. So that's the challenge. So if we go and look at a control volume, this is a fixed volume in space. We have mass coming in and mass coming out. Let's just keep it simple now and only show one port coming in and one port going out. This control volume, the amount of entropy inside this control volume, would be equal to ds system dt. So this accounts for, there could be a rate of change of entropy in the mass that happens to be in there at some instant in time. So let's just think about some instant in time. There's some mass that's inside there. If you were to take a snapshot, that actually could be changing with respect to time. Maybe the control volume is growing, maybe it's heating up. It's just not in a steady state situation. So that is heating up, potentially not in a steady state situation. So that could be, there could be some entropy generation in the mass itself, but also there's more mass coming in at some rate, so that contributes to the control volume, the amount of entropy in this space. There's also some leaving, so that takes away from the amount of entropy in this control volume. Okay, so this d system dt is the same d system dt in the closed system up above, right? So we're basically going to say, let's consider the mass inside the control volume at some instant in time as our closed system. And we're going to take that, so solve this equation for that, and then put that in our closed system analysis up above. And in the end, so we're going to solve this equation for ds dt, take that expression and substitute into the closed system second law expression. So if we do that algebra, we're just making a substitution for this. Again, this is the second law. This is sigma isolated, sigma dot isolated. This is the second law. Make a substitution for that, and we end up with this equation. So all of this is what got substituted. All of this now replaces that. And so in this equation, we don't have a reference to S system anymore. We have a reference to S control volume and the rates at which things are coming in and out of the control volume. Alright, so this is the same thing as sigma dot isolated, and that is a rate now. This is a entropy production rate. If it's in steady state, then this term will cross out, will be gone. And then so instead of the delta S term analogous to that, you have an m dot times S term. So you have, now the interesting thing is that, notice, because of the algebra we went through to replace this d system dt, is that it's m dot s exit is the positive, m dot s in is actually on the negative. So this is kind of reversed of what we had for an energy balance. Okay, so that's the system that we're going to apply in, or the equation that we're going to apply for the second law for open systems. For open transient devices, we could integrate above. You're not responsible for that. We're not going to do open transient analysis. We're only going to do steady devices. So we'll consider these up above, and that term is going to not be significant for steady operating devices. Okay, so I'm just showing you these equations again. You might take time to pause and write these equations out. For open steady systems, sigma dot isolated, right, is equal to, this term is going to be 0 if it's steady, summation of m dot exiting S exit at the exits. So you got to consider the sum of all the exits and the associated mass flow rate. Same thing as the inlets, it's minus that at the inlets, minus sigma. So the minus the summation, you need Q dot system divided by the temperature of the surroundings. So that surroundings connects with the delta S isolated, or the total entropy generation rate. We could replace that temperature of the surroundings with the temperature of the boundary, in which case we would just call that sigma dot for the control volume, so that this would only be what's occurring in the control volume. This is what's occurring in the control volume and in the immediate surroundings. Use whichever one is convenient. Both of those have to be greater than or equal to 0 for the second law. So notice that every term in here is now a rate. Alright, so that's going to be a kilojoule per kilogram per second. Kilojoule per kilogram would be entropy, and it's a rate basis, so now that's per second. Alright, so that would be the same thing as a kilowatt per K, or a BTU per hour per K. Now, by comparison to closed systems, right, or sigma isolated, delta S here minus Q over T. These are not rates. There's no rates here. It does look similar in that, especially if this is a single stream, that you would apply up here. That's an M times a S2 minus S1. Up here, this would be an M dot times a S2 minus an S1 for a single stream. The difference is this one is a mass, and up here it's an M dot, so that's a mass flow rate. There's also a Q here, and up here it's a Q dot. So no rates in this version of the equation, but the equations are very similar in appearance. Okay, so let's work some examples. So what I'm going to do to work these examples is I'll write the equations and then show you the results. So we'll take our time. That'll keep me paced as I go through to explain this, but also we won't waste time with the computation, so I'll just give you the answers. Okay, so steam enters a turbine at 5 megapascals, 450 degrees C, leaves at 1.4 megapascals. So comes in at a high pressure, leaves at a low pressure. Determine the maximum work output per unit mass, neglecting kinetic and potential energy for, in one case, if it's adiabatic, and in another case, if it's cooled at 20 kilojoules per kilogram. So they're going to give us so if you divide, remember, by m dot, you can do an analysis per mass flowing through the turbine. So this is a steam turbine. State 1 is defined. I have a pressure and a temperature. At the exit, they only give us a pressure. They don't tell us what the temperature at the exit is. State 2 is not defined, but they're asking us to find the maximum work. So we're going to choose T2 so that we end up with the maximum possible theoretical work that could come out of this turbine. And we're going to do it for two situations. One, in an adiabatic case, so we're going to neglect the heat transfer from the turbine. And then we'll repeat the analysis. But the second time, assuming that there is a cooling, so Q is negative, it would be coming out in that case. And so we're looking for this. I have this as a little w dot, right? So little w is actually the power per m dot flowing, and the two rates cancel to make this, in the end, this will end up being a kilojoule per kilogram. But it's still a comparison of the rates. It's the power divided by the mass flow rate. Same thing for Q. That Q, little q, is actually Q dot. Let's make that a definition, divided by m dot. Okay, so let's first look at the first law. Well, actually, let's do conservation of mass. At least write it down. Conservation of mass, I'm just going to abbreviate it to say we have an m dot at 1 that's coming in. That has to equal m dot at 2 if it's in steady state. So we're just going to call that an m dot. Right, and our explanation for this is it's going to be, there's a steady single stream. Or you could just reduce the general equation, but this actually communicates our analysis of conservation of mass. Okay, so now let's do the first law. So we'll just write it out. Summation of m dot n h, the kinetic energy plus the potential energy per unit mass. That again minus m dot exit h, 1/2 the velocity squared, plus gz, plus q dot minus w dot equals 0. Equals 0 because it's in steady state, so that right hand side is gone. We don't have any information about kinetic and potential energy. In fact, it says neglect that, so we're going to neglect those changes in kinetic and potential energy. So I'll write that up here. Neglecting delta kinetic energy and delta potential energy. One inlet and one exit. So we're left with m dot h1. Remember, there's only one m dot, minus that same m dot times h2 for this term, plus q dot minus w dot equals 0. Okay, so we're looking for the power, so we're going to solve this for w dot. W dot is equal to q dot plus m dot h1 minus h2. Did I do that right? Take that to the other side, it becomes positive. Okay, so far we have, now we're given that we're working this problem per unit mass, right? So we're going to take that equation, divide by the unknown m dot, so we can solve this to be w equals q plus h1 minus h2. And this is convenient because if we're doing analysis this way, now we can size the turbine just by deciding what is the m dot going to be to get a final power number rather than a power per unit mass. Okay, so we have a couple options for that, a case A and a case B. State 1 is defined. State 2 is not defined, right? So we're going to choose state 2 for max power. Choose T2 for maximum theoretically possible W. And so we'll use the second law to do that. So let's continue on and write down the second law equation. Okay, for the second law, I'm going to use sigma dot isolated. This is equal to, you don't have to show this term, I'm just going to remind myself that it exists, but it's steady, so that's going to be gone, plus the summation, its exit comes first, minus what's coming in for an inlet, minus the summation of Q dot system over T surroundings, so that's got to be greater than or equal to 0, one inlet and one exit. Alright, so there'll just be an m dot that factors out of that. The exit is 2, the inlet is 1, and there's only one heat transfer. So we'll end up with sigma dot isolated is equal to m dot S2 minus S1 minus Q dot divided by T surrounding for this problem. Again, we're not given m dot, so we're going to divide through by that m dot. So we'll end up with sigma isolated dot over an m dot is equal to S2 minus S1 minus this capital Q becomes a little q over T surroundings, right? So that little q again, that's Q dot divided by an m dot. So the rates there, the dimensions of the rates cancel. Okay, so this is greater than or equal to 0, right? Dividing by m dot, we can still use this because m dot is a positive number. So this will still must be greater than or equal to 0 according to the second law. Okay, so now if we had state 2 defined, we could actually evaluate both of these, right? If I had a temperature at state 2, I could substitute, solve for W, and then we could substitute down here and check, make sure it doesn't violate the second law. But when they're asking for the maximum, what we're going to do is push the limits and force this to be reversible, right? So we're going to set this equal to 0, and then solve that for the temperature to define state 2. Alright, so setting this equal to 0 then, we're going to, let's call it force. Force sigma dot isolated to 0 to find T2 for W max. Okay, so if we're going to set this equal to 0, S2 minus S1 minus Q over T surroundings is equal to 0. So we're going to solve this for S2. So these go to the other side of the equation. S2 is equal to S1 plus Q over T surroundings. And remember that state 1 is defined. Right? Q is, we have a case A and a case B, two different situations for this, and temperature of the, we now need a temperature of the surroundings. So what did they give us for a temperature of the surroundings? I don't even think they gave us a temperature of the surroundings. So we'll just have to make an assumption for the temperature of the surroundings. We're going to assume, let me use the numbers that I used here. For the temperature of the surroundings, I used 293 K. So what is that? 20 degrees. 20 degrees C, 293 K. So that's our assumption. So it's an interesting thing that the maximum power that you can get out of a device actually depends on the temperature of the surroundings, which actually is true. It turns out, well, I'll go into some more side discussion and examples of real-world applications of this in the Zoom session. Okay, so now that's how to work this problem. Now go back and look at the numbers. There's the energy balance that we just performed, the first law, and the second law analysis we went through to end up with an expression for S2 for the reversible case. And then for case A, if it's adiabatic for case A, then S2 is equal to S1, so that's the isentropic case. State 1 is defined, and so we have an S1 value, and now with this value for S2 and the pressure, we can actually get an H2. Now I'm calling this H2S and T2S. That little S is because it's for the isentropic case, right? We're saying S2 equals to S1. So we're looking for our optimal situation, reversible case. Okay, so then with our new H2 value, we can substitute that here for H2. Q is 0, and so we get a value for the maximum possible work, or excuse me, power per unit mass flowing through the device. Go to case B, and so we'll use the same equation again. S2 equals S1 minus the Q. This time this Q system doesn't disappear. It's not 0. This is a minus 20 kilojoules per kilogram. Temperature of the surroundings is that 293. Alright, so now S2 is not equal to S1. It's a different value, but we can use that S2 value and the pressure to define state 2, so we can come up with an H2 and a T2 through property evaluations at the exit. So take that H2 and substitute. This time we have to remember there's a Q value to substitute here. Q is minus, so there's a minus, that minus 20, there's the two values of H, and so we end up with 367 can be generated while we're cooling the turbine. Okay. So that is the first example. We'll do the same technique for another example. I'm going to, if I can, find some paper, cover up the solution. Okay, so in this problem we have a device, and they're not telling us the direction. We have power being produced. This is a well-insulated device, so no heat transfer. Air, so it's an ideal gas. Air is either coming in at this pressure and going out at that pressure and temperature, or the reverse case. We don't know which way. And remember, the first law kind of doesn't tell us which way. We're going to have to use the second law to figure out which way. So we have air, so we know it's going to be an ideal gas. We have an m dot given to us, 10 kilograms per second. It's adiabatic. They do give us a velocity. We're going to neglect the change in potential energy and assume that this is horizontal. They have it drawn such that it's horizontal. And so we're going to find W dot and the direction of this. So we're going to get a magnitude for the power. It's either into or out of the system. That will be determined by the direction. So we'll check the second law to come up with the direction. Remember, when I first introduced the idea of the second law, we said that it will predict the direction of a device, whereas the first law cannot predict direction. You can multiply the first law by a minus sign and everything still holds. If you do that to the second law, you just converted a possible device into an impossible device. Okay, so a mechanical engineer might look at this and say, oh, here's the pressure is 1 bar, and over here the pressure is 5 bar, therefore the pressure has to go from high to low, so that dictates the direction. That's actually not the case, because what about for a diffuser? Diffuser is certainly from a low pressure to a high pressure. So we don't know if this is a effective diffuser with a power connection somehow, or effective nozzle with a power connection somehow. We're not sure which way. So we need to do a little bit more than that to show which way the device is going. Okay, so here's what we're going to do. We are going to assume that the flow is from left to right, because that's the way we read. It's just kind of convenient. I'm going to assume the flow goes from 1 to 2. So identify this as the inlet. And then I'm going to work the problem checking the second law. If the second law shows that the entropy production is negative, then I know I've chosen the wrong direction and the actual process is going from 2 to 1. And then if you repeat the second law analysis, assuming that you're going from 2 to 1, you'll get exactly the same result with a different sign, showing that entropy production is positive. Okay, so that's how we're going to do it. The first law will then give us W dot. Okay, so we'll write out the first law first. Oh yeah, first of all, let's do conservation of mass again. Let's do it this way. Conservation of mass. We have a single stream and a steady flow. Okay, so m dot 1 equals m dot 2. So we just have a single m dot that they give us as 10 kilograms per second. Sorry, m dot 1 is equal to m dot 2, 10 kilograms per second. The first law, summation of m dot n, h plus 1/2 the velocity squared plus gz minus m dot exit, h plus 1/2 the velocity squared plus gz plus q dot minus w dot equals 0. So this in steady state, that is going to be 0. It's adiabatic. It's given to us. It says to neglect the potential energy. Neglecting delta potential energy, not the kinetic energy, is given. One inlet, and I missed the summation right there, one exit. Alright, I should have a summation right there that is going to cross out. Alright, so we end up with m dot h1 plus 1/2 the velocity at 1 squared minus m dot h2 plus 1/2 the velocity at 2 squared minus w dot equals to 0. We're looking for the power, right? So w dot is equal to m dot h1 minus h2 plus 1/2 the velocity at 1 squared minus 1/2 the velocity at 2 squared. Remember the units conversion between these is necessary. 1 minus 2 and 1 minus 2. I factored out the m for this, which we have. Okay, so the states are defined and we have those values. Alright, so we can come up with w dot. Now if we assume flow is going from 1 to 2, this is one, that'll give us one answer. If we're wrong and the flow is actually from 2 to 1, right, then w dot is actually the opposite sign. That just reverses 1 and 2 of all of these and changes the sign of the w dot. So now let's get the direction from the second law. Okay, for the second law, we're going to write sigma dot isolated ds control volume dt's in steady state plus the summation of m dot s exit minus the summation of m dot sn minus the summation of q dot over t surroundings. So that's got to be greater than or equal to 0. It's adiabatic, so that's gone. I don't need to know the temperature of the surroundings for this one. One inlet, one exit, so it turns out sigma dot isolated is equal to m dot s2 minus s1. Alright, so that has to be greater than or equal to 0. Okay, so this is an ideal gas, right? So this is air. So we can't evaluate an S1 or S2. We're going to evaluate S2 naught minus S1 naught minus R. Natural log of P2 over P1. Okay, so we've got an assumption that we're moving from left to right. So this is associated, that pressure and that temperature is for state 2. This pressure and temperature is for state 1. We can use those temperatures and temperatures to get a S2 and a S1 and then a P2 and a P1. We can substitute, we can evaluate this, and we'll either get a positive or a negative number. If it is negative, we've assumed the wrong direction. If it's positive, we have the correct direction. Alright, so now let's take a look at the numbers. For it looks like I did the second law first, so here's that same equation we had arrived at. Right, that would be sigma dot isolated. I divided by the m dot, and I'm just evaluating that entropy change to check whether or not it is positive or negative. So we have to look up an S2 and S1, substitute. This turns out to be negative. So the assumption that the flow goes from left to right is not physically possible. That violates the second law. And so what we could do is now repeat the analysis, assuming the flow goes from 2 to 1, in which case we would end up, let's go back to here, we'll end up with this, right? Only we'll reverse the pressure and the temperature and reverse these two. What you'll end up with is the same exact number, except it's going to be positive. So no need to go through and do all that work. If you assume the flow goes the other way, we'll end up with that positive number. And then we can assume that, hey, our direction was chosen correctly, actually. So the flow goes from right to left. So it is correct that it goes from a high pressure to a low pressure in this case, but we have verified it with the second law. Okay, so now with that information, we can go and evaluate the first law. Alright, so we evaluate the first law. And now we're assuming the flow is from 2 to 1. Right, so the inlet, I have 2's here. The exit, I have 1's there. So this is the negative of the numbers that we had in the previous equation. If we substitute in numbers for that, we get minus 1741.5 kilowatts. So this device consumes power. Even though the flow has an advantageous pressure gradient. So the truth is, from a mechanical engineering perspective, this device doesn't have much use, but that wasn't the point of it. The point was to give us something to apply the first law and the second law and evaluate. Okay, so now what I want to do is discuss just 2 of your homework problems. Actually, the first one that I'm going to discuss is problem 79. It's actually very similar to the first example we worked. A well-insulated turbine. It's air though instead of steam, but a well-insulated turbine. High pressure and temperature air, 1400 K, 8 bar come in. It leaves at 0.8 bar, so much lower pressure. They don't specify the temperature, then they ask us for what's the maximum theoretical possible power. So we're going to choose T2 for the maximum power output, and we're also working this problem per unit mass, so we're dividing W dot by M dot. And you're doing it for the insulated case. So this is very, very similar to the first part A of the first example that we worked today. Do your energy balance if we're neglecting kinetic and potential energies. It's adiabatic, so we're only left with the H of these two. There's only one M dot that can be factored out and divided through. Solve this for W dot. Solve this for W dot over M dot. So little w is just the change in enthalpy. State 1 is defined. State 2, we need a T2, and we'll use the second law to force the process to be reversible to get the maximum power. That'll define our state 2. So the second law, sigma isolated, is equal to, there's the second law equation. Alright, steady state, so that's gone. 1 exit and 1 inlet. It's adiabatic, that term is gone, so we're left with just M dot is S2 minus S1. Alright, okay, so to force the maximum power, we're going to set this sigma dot isolated equal to 0. Alright, so that means S2 has to be equal to S1, so we're going to say it's an isentropic process. So state 1 is defined. We can come up with a value for S1. Now, actually, this is air, so pardon me. This is air, so we can't come up with an S1 or an S2. Since it is air, we have to evaluate delta S with our equation, right? S2 naught minus S1, all of this is our delta S. Set that equal to 0 and solve it for the standard state entropy at 2. Right, so we'll come up with, we can compute, we have state 1 defined, so we can look that up in the table, evaluate this, we have the pressures at both states, get a number for this, and then come out of the table with the temperature and the H at state 2, which we can then use to go back and calculate our maximum amount of work. So that's how you go about solving this problem. That's the theory. That's problem 79. Very similar to the first example that we worked. You have a couple other examples that are also very, very similar, so I'm going to let you work those for experience. And I'm going to skip to your last problem in your homework assignment is 102. This one actually has some heat transfer. So I want to work an example that involves some heat transfer. I'll say problem 102, we have a steam turbine in this case. So high pressure steam, high pressure and high temperature. They give us a mass flow rate, although it's in kilograms per minute. Convert that to kilograms per second. There's my note that it's steam. Goes out at a much, much lower pressure, and the quality happens to be equal to 1. So this has much, much less internal energy or enthalpy than what's coming in at 1. We're hoping the difference between that will produce a lot of power. So the power they're giving us is 2 megawatts, and then they're asking for the heat transfer. I'm assuming T ambient is 27 degrees C for 300 K. The problem asks for Q dot, and then it also asks for the rate of entropy production in a composite system, meaning the turbine plus the immediate surroundings. So we know that to be sigma dot isolated, or the total entropy production. So they made a wordy problem statement, but what they're really asking for is the rate of total entropy production. All right, so that's just sigma dot isolated. To do your conservation of mass, do something to communicate it. I know it's so trivial, you're going to say, oh yeah, it's the same m dot through this whole device, but at least write that down, that you're making that assumption because it's steady state. All right, and then do a second law. Sorry, first law. I'm going to do the first law. We're neglecting kinetic and potential energies. One inlet, one exit. We have to keep both of these, right? They're asking for Q and they're giving us the W dot. It's steady state, so the right hand side is gone. So this is all we're left with. This coming in, M dot H1. M dot H2 is leaving, so there's a minus, plus Q minus W dot. Solve this for Q, so we'll do the algebra. Take W dot and these two to the other side. So this H1 minus H2, when I take it to the other side, becomes a H2 minus H1. Okay, so in this case, both states are defined. Right, I have a state 1, so we can get an H1. State 2 is defined. M dot is given. The power is given. We can substitute in numbers, make sure units are correct. You should end up with minus 184.8 kilowatts. It's a minus, so it's out of the system. Okay, so now we're going to evaluate the second law. We want to know what is sigma dot isolated, the rate of total entropy production. So this is our entropy balance formula then. ds, control volume dt is 0 because we're in steady state. Right, there's only one inlet, so m dot S2 is coming in, exiting. Exit comes first, then the inlet, minus m dot S1 is the inlet. One heat transfer, so this will be Q dot over temperature of the surroundings. Okay, so now we just need to evaluate this. Right, the states are defined. You can get S1 and S2. M dot is given. We just calculated Q dot above. This is the temperature of the surroundings, given as 27 degrees, so 300 K. It has to be an absolute. If you substitute values and do the computations, you'll end up with 2.16 kilojoules per Ks, or a kilojoule per second is a kilowatt, so that's a kilowatt per K. And they didn't ask us to make the conclusion, but since this is a positive number, then that says this device is theoretically possible. Okay, that concludes all of the topics that we're going to discuss in the class. So the last topics on an entropy balance in chapter 6, let me go find that kind of summary. So kind of the last exam is going to focus on this. Either you're going to have an open system and you need to start with this second law as part of your analysis. You still might have to do a first law in conservation of mass for open steady devices. But this is, you'll start with one of these two. Inevitably, I think I'm going to give you the temperature of the surroundings. I don't like doing the boundary temperature, so you'll start. I'll go ahead and tell you, you'll start with this one. If it's a steady, open steady situation. If it's a closed system, then you'll use this one. We'll use sigma isolated. I'll give you the temperature of the surroundings again. If it's an open steady single stream, if you notice, the equations would be very, very similar. In fact, let me write them out. So an open steady single stream, the equation would be sigma dot isolated is equal to m dot S2 minus S1 minus Q dot over temperature of the surroundings is greater than or equal to 0. Single stream. If it's an if it's a closed system, though, we would have sigma isolated is equal to m S2 minus S1 minus Q over T surroundings is greater than or equal to 0. So you see how very, very similar these look. Open, steady. It looks like this with a single stream. Open, steady, single stream. Right, and this is closed. Going from state 1 to state 2. Look how similar these equations are. The only difference is this is a rate and that's a rate. Right, all these, this is the exact same of the equation except in the form of a rate. And if you think about it, if you have a device with a single stream, you can think of considering the mass as it enters our steadily operating device. That as it enters, that mass comes in at one state, goes through the device, and then goes out at another state. So we can think of it as a closed system transferring through the device from a state 1 to a state 2. So technically, you could get away with a single stream device using this one. However, I'm asking you to identify that for an open, steady device, start with the appropriate base equation, because inevitably what students do is they'll start with some version of this and then have a dot here too or something. Something will be some mixed form. Don't mix these two. And so to keep you from doing that, I'm going to insist that if it's an open steady device, you start with the open steady base equations. Always start with the basic equation for the appropriate type of system you're analyzing. It's either closed or it's an open steady device. Identify that at the very beginning of your solutions and then reduce the equations appropriately. Right, so let's see if we can get all of those. There's all the equations that you'll need. Actually, I've already told you that you're only going to need the first equations of each of those for the final exam. You're only going to need that equation and that equation for the second law part. Okay, so I hope it was still a good course. I know there was a lot that we discussed at the very end regarding the second law. Your entire discussion of the second law came to you via online and through these videos. Hopefully you still get some value from what you've learned in the class. Good luck on your final.